So let's start with this structure for commercial photovoltaic cells. What I want to highlight to you is that you see this is N++ P, which N++ is the N heavily doped N-type silicon. P is the P-type silicon. When you put the two materials together, they have the P-N junction here. As in the lecture, Dan mentioned about how does the P-N junction work, charge separation contributing to the current. So the very important feature of a solar cell is this P-N junction. With this P-N junction, you can separate the charges generated by the light, and you can have the electricity. So if you want to have a physical picture of how does this photovoltaics work, this is what I was talking about. You have N-type materials, P-type materials. When you put them two together, they establish this P-N junction here, which can separate charge. So let me walk through this with you step by step. So because for the P-type materials, you have the excess holes, the positive charges, the holes, and then the N-type materials, you have the excess free electrons. Because there is a concentration difference between them, you can see the schematically that the electrons will diffuse towards the left, leaving these positive charged ions, and the holes will diffuse to the right, leaving these negative charged ions. And these ions will establish an electric field like this towards the right. So when the light hits your material, it gets absorbed, generating these holes and electrons. They will get separated by this electric field. So this is essentially how does this work. So photovoltaics, it has two steps. First, you need to absorb the light, generate the charges. Secondly, and very important, you need to separate them into different directions, contributing to the current. And this is how this works. And you can get deeper into, have the readings, you can go deeper into this like Venn diagram, Fermi level, etc. But the takeaway message is this absorption and then this charge separation, and then you have a photovoltaic cells. And this is another one talking about the IV curve. So if you talk about photovoltaics, then people expect you to know something about IV curve. The photovoltaic cell we talk about, they can be modeled in an electric circuit as this current source as well as a diode here. And if you model this guy here, you will end up with some IV curve like this. This is the current, this is the voltage. Essentially, when you have different voltage here, you have different currents. And this black line is the ideal case. Let's focus on this one. You see the ideal IV curve is very similar to a kind of square box. And how close this is to a square box is called fill factor, where you can pick one point along this line, give you the maximum power. I hope you remember that power equals to voltage multiplied by the current, right? So along this line, there is one point, give you the maximum power. And if you use the maximum power divided by the open circuit current, or open circuit voltage, the maximum voltage you can get, and the short circuit current, the maximum current you can get. And if you divide that, that's the fill factor we're talking about. So you see, fill factor of 1, the square will be optimal, but because of the physics there, the ideal one cannot even go to 1. You can kind of think about this analogous to like the capacity factor we're talking about. So the power plant will not typically work like 24/7. And also the solar cell will not be able to produce the maximum current and maximum voltage like that. So you only somewhere along this line here. So this is a good point when we talk about efficiency loss mechanism. One of the mechanisms is that in real practice, your photovoltaic cells will not be able to operating at the maximum power point here. They may be operating somewhere here or here, therefore not the maximum one, and give you some kind of efficiency loss because it's non-optimal operating point. And also in your solar panels, there might be some parallel resistance leaking the currents, not going through your load, but leaking through here. And you may also have some series resistance here, having some loss from there as well. And we did this kind of losses previously, right? And this gives you a picture of other, like physics, in terms of from the physics picture, what are the other efficiency loss mechanisms here? What shows you here is the solar spectrum. On the y-axis is how many photons for particular wavelengths of light. So the solar AM1.5, the solar spectrum go all the way here, but we cut off the infrared portion like that because for silicon, the band gap is 1.1 electron volts, which is about 1100 nanometer in wavelengths. So any lights longer than 1100 nanometer, they cannot be absorbed by solar cells. So those are like called infrared losses, contributing to lower currents, contributing to efficiency loss. And you may ask, why not have a lower band gap materials where you can absorb this portion as well? But the problem is that by having a lower band gap materials, although you can absorb a larger portion of the spectrum, but the voltage will be lower. And because of the thermalization loss. What I'm talking about here is that if you have think about if you have a smaller band gap between the conduction band and the valence band, a smaller band gap, this open circuit voltage you can establish will be kind of proportionally lower as well. So therefore, in this picture, if you have a lower band gap materials, your open circuit voltage will also be lower. So lower voltage also leads to a lower efficiency. So there is a trade-off there. So Dan showed you in the lecture that what is the maximum efficiency with respect to different band gap, right? So silicon with 1.1 electron volts happens to be very close to the optimal band gap. And this is how it absorbs the light. So besides the band gap, the thickness of the materials also matters, because if you do not have thick enough materials, it does not have complete absorption, such as here. What I shows you here is for different thickness of silicon, how well it absorbs this AM1.5 spectrum. So as you see that the purple one is for 1 micron of thickness. As you increase the thickness, it absorbs this visible range from 400 nanometer to 800 nanometer is the visible spectrum. They absorb it more and more. The black one is for the 300 micrometer thickness, which is a typical commercial solar cell thickness. It absorbs all of the visible range and absorbs a significant portion of the infrared range as well. Okay, so what I'm talking about here is that you see, if you have infinite thickness, you should be able to absorb everything below 1100 nanometer wavelengths. But it's not happening here because of the absorption coefficient issue. And the fourth one, also related optically, is the surface reflection. When the light comes into a surface, it reflects portion of the light, and so only portion of this AM1.5 actually goes into your materials and is available for absorption. Okay, so those are the efficiency loss mechanism there. And what you see here, this graph shows you the simulation of, for different thickness, what is the photocurrent you can generate. It basically just tells you that when you increase the thickness, you have a larger and larger photocurrent, but at a certain point, it doesn't quite make a difference. It kind of flattens out eventually. And the black dot here is 300 micrometer, the commercial photovoltaic solar cell thickness. Okay, so those are the physics, and now let's look at how do people actually make them commercially. This architecture I showed you previously, and let's review it again. This pyramid on the top surface is called a surface tempering. What this guy does is that it reduces your reflection. So you have more light comes into your p-n junction and gets absorbed and the charge gets separated. And then you have to have this p-n junction here. And what you do is you doping them in a very high temperature furnace and then doping p-type into n-type, providing this p-n junction. And also you do some thin film deposition on the top surface to further enhance your anti-reflection as well as passivating your surface to reduce the recombination. And also you need to make the contacts at the front and the back so that when the charge gets separated, you can connect them and becomes, deliver them to your external node. So these are some pictures shows you the flow. The first one is surface texturing. Basically, you put the wafers here, square, into some chemical bath. The chemicals will etch the front surface into this kind of pyramids here, and that's for surface texturing. And then you put them into the furnace, high temperature one, and then the phosphorus atoms there will diffuse into the surface of your wafer, making this N++ area, and then you establish p-n junction. But because you have the N junction everywhere on the surface of your wafer, you would like to cut off the edges so that you do not link your N junction here with your backside. So this is the edge isolation, the next step. Then after that, I mentioned about that you have you deposit some very thin films, a few nanometers of film, which can help with your anti-reflection as well as surface passivation to further improve the performance. And then this screen printing of electric contact. Typically, these contacts are silver. What they does, the screen printing is that they have some kind of screen there, have some opening, and then you put the silver paste through the screen, and where you have opening, they drops here, and you have the contact like that. And also you have back contact. After you have print them, you put them into furnace again to firing at high temperature to activate the contact, kind of improve the ohmic contact between your metal contact here with your silicon materials to reduce the series resistance we talk about here, series resistance, right? Firing contact, etc. Okay, so that is making the module. After making the module, you want to test each of that's making the solar cell. So after making the solar cell, you want to test the efficiency of each individual one and bin them according to their efficiency. And then you want to string them in series for the similar efficiency solar cells together. This manually in Suntech is from the one news report. After you string them together, you put this string solar cells on a glass, and you put some polymer to laminate them and put the front glass. Then now you have the solar panels. So that's kind of the process flow for commercially how do they make solar cells in China. And then this is another technology we mentioned about cadmium telluride thin film PV modules. It's different from silicon wafer. It's very thin. It starts with the glass, and typically the glass comes with something called TCO, the transparent conducting oxide. So this layer, they can conduct electricity, but they're almost transparent to light. So in operation, the light will come from this direction. And you deposit your semiconductor, the absorber materials on top of this glass, and then you use laser to scribe some openings, and then you put your back contact there. So now you have your front contact, back contact, and you have your p-n junction here, and that's a solar cell. That's for the cadmium telluride process flow. This appeared in your provinces. I hope you saw it. That's for silicon wafer technology, and the red triangles are for the cadmium telluride thin film technology. What it shows you is that over the years, as we produce more and more of them, and we innovated more and more, and optimize the process more and more, the cost reduces. In 1976, it's a few, like $60 per watt. And those are mainly used for satellite applications. For those of you who watched the movie Interstellar, right, their space shuttle, they have the solar panels there, if you pay attention. I paid attention. So back then, they are very expensive. They are almost just for satellite applications. But as we continue to innovate, the cost goes down. And also the scale of production each year, they went up. So you have the economy of scale, and the value chain gets better, along the more synergies, and then the cost drops. This is for thin film. The first solar started their large-scale commercial production somewhere in 2006, and back then it's about $2 per watt. As they produce more and more over the past almost 10 years, their cost drops almost to like 60 cents per watt in the fourth quarter of 2013. this is the learning curve. And the rationale behind this learning curve, I think now you all know, right? We tested it, why cost went down. So the kind of typical rationale people use for the photovoltaic industry is that because of this learning curve, if countries continue to put more public funding, we are able to see larger production, and along this we can also have more innovations. The cost will go down magically. Okay, this is another concept of thin film crystalline silicon. Please ask questions anywhere, if you are not clear. This thin film one is like, although 3 micrometer of silicon cannot absorb the light completely, but if you somehow have some advanced structure on the top and on the back, so you can trap the light. Once the light comes in, it cannot get out. It traps, bounces between the top and bottom multiple times. Effectively, you increase the thickness and you can increase the absorption as well. That's one still in research phase. Okay. Now we move to installation. This is one picture I took in Boston while attending a conference in 2012. What do you spot? What's wrong here? Relation to the sun and the solar panel. Yeah, it's facing the wrong direction, right? So I was taking the subway there, waiting for the train, and I was looking at the solar panel. Why it's facing me, not facing the sun, right? After that, then I did some side project on the optimization of PV installation. And the rule of thumb currently people have is that you face your solar panel towards the south. In the United States, you face them towards the south. And the tilt angle, you see they're tilted, they're not flat sitting there, but they're tilted for a certain angle. The tilt angle is almost equal to the latitude. For example, in Berkeley, it's somewhere around 38 degrees north. So you tilt your panels by 38 degrees. That can give you the optimal annual efficiency. But this is not, a better one is that if you are able to change the panel angle once a year, the best one is that actually, then you need actually twice a year because change it and change it back, right? Twice a year, then it actually can improve your efficiency by 20% as well. Because this rule of thumb is based on the annual installation. They are not optimized for summer or winter. Because this figure shows you that in the summer, some places in the United States, you can almost have perpendicular angle of incidence during noon, but in winter you cannot. So you need different angles to optimize for them. What I want you to understand from this picture is that there is something called angle of incidence. Basically, what is the angle comes in onto your solar panels. Another thing is called air mass. Like I mentioned previously, AM1.5. What does AM1.5 mean? It's called air mass 1.5. So this is AM0. Here, outside of the atmosphere, in AM0, there is no air above it, so air mass 0. If the sun comes perpendicularly, angle of incidence 0, the air mass is 1.0. At the angle of 48.2 degrees, the air mass, the length is about 1.5 times of this one, so it's called air mass 1.5, AM 1.5, something you need to know about.
Isn't that graph kind of misleading though, because doesn't the atmosphere bend the light?
Bends the light? That's a good question, but not that much. This is kind of schematics, not accurate to every detail, but it shows you roughly what is AM 1.5, how do people calculate it. They basically use this kind of angle, the mass of the air, and then do the simulation to show which spectrum gets absorbed, which one can reach the air surface, the Earth's surface. So this is the last portion about the policy one, is that the PV industry has become a global industry that along the value chain of R&D, manufacturing and installation, each country are particularly strong in one step along the chain. So if you look at this graph, it shows you United States, China, Japan, and Germany. And these bars are for the installation. here, the market size. And this radar plot, it shows you the relative share among the 4 countries in terms of patents, innovation, manufacturing, who make the solar cells, and the market, who installed the solar cells. What you can see is that in 2000s, Japan is strong in every axis. They produce a lot of patents, innovate. They also manufacture a lot of them, and most of them also gets installed within Japan market size. United States is a major innovator back then and has some market and some manufacturing as well. And Germany innovates quite big back then. So what happened between these 10 years is that the industry scaled up dramatically. If you see this curve, back then, in most of the countries, the market size almost not noticeable compared with now. Right? It scaled up dramatically over these 10, 12 years. And what happened in 2010 is if we take a snapshot, US is a major player in innovation, produce a lot of patents in this first value chain, but doesn't have significant market size or manufacturing. China make a lot of solar panels back in 2010, but does not have a significant market, or it doesn't produce much patents. Germany back in 2010 is a leading world's largest solar market. But you see, ironically is that their innovation share drops. And they also doesn't make that much compared with what they install. And Japan, not very, compared with others, it's not very interesting is their share kind of just shrinks in every direction. And they still innovate, but in terms of market size and manufacturing, it shrinks. So there is not much new initiative went on between 2000 and 2010 for Japan. But for 2013, Japan has new feed-in tariff incentives, so their market size increases again. So this is the picture here. What's the key message I want you to take away is that the photovoltaic industry is truly a globalized industry. Some countries are very focused on innovation, or maybe that's the only thing left for them to do. Some countries make a lot of dominate the manufacturing, and some countries dominate the market, but they are evolving as well. What I want to show you is that what leads us to do that innovation paper is that if you look at Germany and relates this to learning curve, the theory is that if you put more money, you encourage more markets installation, right? You can also encourage people to manufacture them and also to do innovation, right? But what happened in Germany, what you can see is that they increased their market size dramatically. But what didn't happen is the scale up of manufacturing as well as the innovation. Their innovation share even went down. So this is some signal showing that this demand pool kind of approach, putting money and hoping that magic will happen, we will have more innovation and cost will go down, seems not to be quite applied here. And this, because I spent my 5 years PhD doing photovoltaics, it's better for me to know what is going on in the industry. So what was going on in the industry back in 2011 and 2012 is, this is the net profit for the 9 largest solar companies in the world. They are mostly listed in the United States stock market. So actually the US investors are investing in Chinese companies as well. In 2011 and 2012, you see almost all of them were making a net loss. Particularly, I want to highlight the Suntech. In 2011, Suntech may have a net loss of $1 billion US. Since they were founded, the cumulative net profit they have is $500 million. And in this single year, they lost twice what they have earned. That's what was going on. So in the news, people were talking about, oh, you see the PV manufacturing industry is dead walking because we lack government support. But if you look at this top graph here, the government support for the PV industry is increasing steadily. The top figure is the deployment incentive in amount of $1 billion. You see in the United States, from 2006 and 2012, it's increasing, right? Germany, they are increasing. In 2011, that 1 year, the feed-in tariff payment for Germany is almost 10 billion US dollars. Okay, but it does not correlate with how the manufacturing is performing. So can anyone guess what went wrong? Do you understand what I'm trying to describe here? The kind of problem is that the government is putting more money into PV industry, incentivize installation. But the PV company, the manufacturers are making a net loss here, suffering, dead walking one time in the headlines. But what went wrong? In the previous picture, when you put more money, you should have a vibrant industry. People are producing more, innovate more, cost goes down. Everything should be a rosy picture, right? But here you put in more money, but the industry almost went dead at one point. They kind of recovered in last year, but it's mixed. Half of them are still making a net loss, half of them are making some profits. Anyone guess what went wrong? Okay, seeing that today is not very engaging case.
I just have a question, which is, when you say put money in, do you mean like just gave loans, or the government gave money to the companies, or like what's the format?
The detail is that for the United States, the data you show here is in terms of tax credits.
Okay.
So when you install a system, 30% of the cost can be claimed against your income tax, federal income tax. And then the light blue portion here is the cash grant, enacted in 2009 by the ARRA, the American Recovery and Reinvestment Act. So instead of tax credit, they also give you cash grant.
So it's
under
to
that.
consumers?
To consumers.
Okay.
But the story is that normally consumers are not in a position to claim them. So normally it's like, for example, Solar City, their business model is that they help you claim that 30% tax credit, and you do not need to put any money down. You just sign a contract with Solar City, and every month you pay whatever is generated there at a certain rate. And in Germany, it's called feed-in tariff. So for example, you install a solar panel on a rooftop, although they do not subsidize the initial capital cost, but over the years, every kilowatt hour of electricity you produce, you feed them back to the grid, and they pay you a certain rate.